Hey guys, I've had a couple requests to go over a couple different things we've talked in class but I haven't made videos for. One of them being net ionic equations. I think really what you guys want to do is just really see the process again. So let's kind of talk about what's going on. First off, a net ionic equation is what's showing what's actually occurring in the reaction. Remember when an ionic compound is dissolved or aqueous in solution, it's breaking up into ions. Well, if an ion is an ion on the reactant side and the same ion on the product side, it hasn't changed at all. It's still the same thing as it was to begin with as it is ending with. So therefore, it's not actually reacting. It's not doing anything whatsoever. So we don't show that in our net ionic equation. The net ionic equation is only showing what is reacting. So let's kind of look at one of these. I have reaction here. It says potassium iodide and lead 2 nitrate solutions are mixed together in a beaker. So first off, we're told that they're solutions and we need to write out what they are. So we write out the full reaction. Well, potassium iodide is Ki, and it's aqueous because we're told it's a solution. Then we have lead 2 nitrate, which is Pb, NO3 with parentheses 2, also aqueous because we're told it's a solution. Now, this is a double replacement reaction. We can tell that because we're starting out with 2 compounds and obviously 2 ionic compounds as well, so the ions are switching places. So we'll end up with potassium nitrate, KNO3. Nitrate, sorry, not nitrate, I said the wrong word. And lead iodide, lead 2 iodide specifically because it's a 2 over here as well. So that's our reaction. And let's move this over just a little bit so we can put our state of matter there. So we have PbI2 and state of matter. So what we next need to do is figure out our state of matter of our products. Well, that's going to be done by looking at our solubility rules. And you will get solubility rules on the test. You're not really required to have them memorized anymore for the AP test, so there's no point in making you guys memorize them. However, I still would advise knowing the main ones, knowing the alkali metals are always soluble, knowing halogens are soluble with everything except silver, mercury, and lead. Kind of some of those big ones we use a lot. In this case, we have potassium and nitrate, which are both always aqueous, are always soluble. So this guy's aqueous. And we have lead iodide. So we have a halogen bonded with lead. Well, halogens are soluble with everything except lead, silver, and mercury. So this guy is actually our solid. It's our precipitant. Okay. Once we're done with that, our next step here is to break our compounds into their ions as long as they're aqueous. Aqueous means it is ionizing. Ionizing means it's breaking into ions in solutions. And actually, technically, our first step should be here to balance. Okay, so once it's balanced, then we can separate into our ions. So what we have here, potassium iodide, it is aqueous. So it's going to break down into 2 potassium ions plus 2 iodine ions. And yes, you need to show the charges here. I've had a couple of you guys who will do the charges matter. Yes, they matter. So we do want to put those up there. Okay, that's going to be added to lead nitrate, also aqueous. So we break that up into lead plus 2 ions plus 2 nitrate ions. If you're breaking up a compound that has a numeric value at the end like this, like 2 nitrates, you bring it to the front like a coefficient. Because remember, it is a counting number. It's how many are there. Don't leave it back here. Don't leave nitrate in parentheses with a 2 on the outside of it. We bring it up and saying, oh, there's 2 nitrate ions. Okay, so we draw our arrow. I'm going to enter down to the next line. We have 2 potassium nitrates, aqueous again, so we have 2 potassiums. And again, these are ions, so we write our charge. And 2 nitrates. And again, we write our charge. And last but not least, we have lead iodide, which is a solid. So PbI2, and we keep it together just like that. So that's step 1 and step 2. So let's take this, copy it, and bring it over to our next slide. Because what we want to do is our next step is to cross out all the ions that are on both sides of the equation. So this is why having this charge in here is important. We'll look at one in just a minute where you can have a ion on this side, but over on the other side of the arrow it becomes an element, so it no longer has a charge. So they cannot cancel out. It has to be the exact same thing and the exact same number to be able to cancel out. So for example, 2 potassium ions, 2 potassium ions. They cancel out. Iodide, we have an iodide ion here, but we do not have an iodide ion here. It's actually in the compound, so it is not equal. It cannot be crossed out. Same with the lead. We have a lead ion, but we do not have a lead ion over here. We do, however, have 2 nitrate ions on both sides of the arrow, so those can cross out. So from there, we rewrite it, and I always put my metal back first if I have this type of situation, just because you guys know me. I'm a little OCD, and I like things to be in a specific order. So we have lead plus 2 iodides, and that's reacting to form lead iodide. So that's what's actually happening in the solution. We have everything breaking up into its ions, what we start with, and as these ions interact, potassium and nitrate may very well interact, but they're not going to form a bond to the point where they precipitate because they remain soluble. So potassium nitrate forms, but it's really not forming because it's going to ionize as soon as it's formed. So it really just stays as ions. However, when lead and iodide interact, they are going to interact, and that interaction is going to cause a precipitant because those guys, when they interact, are not going to be soluble. So what we actually have happening is lead ions and iodine ions in solution falling out and forming lead 2 iodide compounds. So this is the actual reaction. Potassium and nitrate staying in solution are not really a part of the reaction at all. They're just kind of more of the transporters for the ions like iodide and lead that are reacting. So let's look at a couple more. Okay? And I just grabbed a couple different ones just because I think what I'm seeing with you guys is you just kind of want to see it done to kind of get the hang of it and figure out what's going on. So we have copper 2 chloride, CuCl2, and it is a solution, so aqueous. We are reacting that with sodium sulfide, so Na2S, and it is also a solution. It's going to form copper 2 sulfide, and the reason it's copper 2 is because sulfur is always a -2 here, and copper is a 2 here because of the 2 here. So we'll put parentheses there because we don't know its state of matter right now, and NaCl state of matter. Now we really can look at NaCl and kind of know, okay, it's aqueous. We got that. Also with balancing, we want a 2 here. But copper sulfide, if we look at our rules for sulfides, most sulfides are insoluble, so this guy's going to be a solid. Okay, so now we break up our things into ions. So we have copper ions plus 2 chlorine ions plus 2 sodiums. Again, notice I'm bringing the 2 up front. I'm not leaving it back there. Plus 1 sulfide ion. That's going to break down into copper sulfide, which stays together, plus 2 sodium ions, plus 2, sorry, I forgot the 2, chlorine ions. So again, we only cross off what's on both sides. Well, copper I don't have on both sides. Chlorine I do, and sodium I do, but I don't with the sulfide. So my final reaction, my net ionic equation is just going to be copper plus 2, sulfur minus 2, forming copper sulfide. Okay, you can do the same thing with the next one. Chlorine gas is Cl2, and it's a gas. It's bubbled into a solution of potassium bromide. So this is a solution, so KBr, aqueous. This is a single replacement reaction, and remember here the nonmetal replaces the nonmetal, so we end up with KCl, aqueous, because it is a alkali metal, and Br2, which is a liquid. So we break up our ions. Again, Cl2 is not aqueous. It is not going to break up. Potassium will, and there should be a 2 here, as well as a 2 here, plus 2 bromine ions, forming 2 potassium ions, plus 2 chlorine ions, plus Br2, which will not break up as well because it's a liquid. So the only thing that cancels out here are our potassiums. So our final reaction is just Cl2 plus 2 Br minus, forming 2 Cl minus plus Br2. Okay, small piece of sodium is placed in a beaker. It should say a beaker of water. Not sure what happened with the water there, but we have Na, and let's go ahead and fix that so that doesn't confuse us. There we go. There's our of water. Sodium's placed in a beaker of water. So we have plus H2O. This is a single replacement reaction where sodium kicks off one of the hydrogens, so we end up with NaOH and H2. And of course, states and matter, this guy is solid. Water obviously is a liquid. Sodium hydroxide is sodium with anything else, so it is aqueous because it's an alkali metal. And we have, of course, gas. So if we break up our ions, sodium can't break up, it's just Na. H2O can't break up, just H2O. Sodium hydroxide can. And again, sorry, I keep forgetting to balance these. My bad, guys. 2, 2, 2 there. So 2 Na plus, and I guess there should be a 2 here. There we go. Plus 2 hydroxide ions, plus H2. Okay, well, if you notice, nothing can cancel out. This is actually our net ionic equation. Okay, same thing with potassium oxide and water. K2O, it's solid, plus H2O, liquid. This again is a synthesis. And in this case, when we have a metal oxide plus water, it forms a metal hydroxide, so this is going to form KOH. KOH is going to be aqueous, because again, alkali metal with hydroxide. So our net ionic equation, which again, sorry, balancing 2 there, is going to be K2O, because it won't break up. H2O forming 2 potassium ions plus 2 hydroxide ions. And our net ionic equation is the same as this right here, because nothing can cancel out. Let's look at a couple more and we'll wrap up the video. Strontium hydroxide, SrOH2, and we're told that it is a solid, plus nitric acid, HNO3, and all acids are aqueous in this case. Okay, it's going to react, double replacement. We're going to end up with strontium nitrate, so SrNO3 2, and nitrates are always aqueous. And water and hydrogen, or sorry, hydroxide and hydrogen, which of course is H2O, which is a liquid. Okay, so when we go through, balance it this time. Let's see if we can remember to balance it. It is not balanced. We need a 2 here and a 2 there. So we break up everything that's aqueous. Well, SrOH here is not aqueous, so it's going to stay just the way it is. Okay, then we're going to have 2 hydrogen ions plus 2 nitrate ions, forming Sr plus 2, plus again 2 NO3s. Again, notice I pull up the 2, I'm not leaving it behind, plus 2 H2O. So the only things that cancel out here are the nitrates. Nothing else can cancel out. So my net ionic equation is just going to be SrOH2 plus 2H plus, forming Sr plus 2 plus 2H2O. Okay. Barium chloride is BaCl2, and it is a solution, so aqueous. It is added drop by drop to solution of sodium carbonate, Na2CO3. Whoops, let's try that again. CO3, and of course this is aqueous because it's a solution, and it's forming a precipitant. They're nice enough to tell us that. So barium and sodium are trading places, so we end up with NaCl. We know it's not going to be our precipitant. And barium carbonate, which of course is our precipitant. Most carbonates are, to most of the time, depending on what they're bonding with, but most of the time. So 2 here, that's done. We break up our ions. We end up with Ba plus 2, plus 2 Cl minus, plus 2 Na plus, plus CO3 minus, forming 2 Na plus 2 Cl minus, plus BaCO3. So the things that are going to cancel out are going to be our chlorines and our sodiums. So our net ionic equation is just Ba plus 2 plus CO3 minus 2 there, forming BaCO3. Okay, so that's kind of it. We can do the last one a little bit later if we need to. Actually, this one's important with the fact that what it forms is something that you guys keep forgetting, which is when carbonic acid is formed, in this case it is, it doesn't actually form H2CO3, it forms H2O and CO2 because it does break down instantaneously. So if we were to do our net ionic equation here, you would have to take into account that those don't break down. And from the looks of it, because this is bubbled, it's a gas, nothing actually is going to cancel out here except for the sodiums. So we'll end it at that. Hopefully this helps. If you have any questions, let me know.